Hi, welcome to our 17th lecture on graduate combinatorics. So today we'll continue discussing the notion of group action, and we'll see how it can be applied to various examples in combinatorics, number theory, and algebra. So as you remember from last lecture, we defined the notion of a group action as follows. We have a group G and a set X, and we say that the group G acts on the set X if there is a map, so a function from the set of order pairs G and X, where G comes from the group G and X comes from the set X, into the set X, that satisfies the following properties. If we map the identity element of the group and the pair between the identity element of the group and any element X, that is mapped to X for any element X of the set X. And the second property is that if the element G of the group acts on the element H acting on X, which is an element, so this one here, it's an element of X, then this is the same as the group product G times G, which is an element of G acting on X. So this map, as I should have mentioned earlier, this map is called a group action. So this the map that is described here, and it satisfies these properties below. So this is this map is group action. All right. Now we proved last time that the binary relation on this is a binary relation on the elements of X, defined as follows: X is equivalent to Y if and only if there is a group element G such that G acting on X produces Y, is an equivalence relation. So this binary relation is reflexive, symmetric, and transitive. And therefore, this equivalence relation is going to produce some equivalence classes, and these equivalence classes are called the orbits of this action. So if we take an element X, so for an element X in X, its orbit, which is known by O of X, consists of all elements of the form G acting on X for G and a group element in G. So this is a subset of X, and from the properties of equivalence relation and equivalence classes, it follows that two orbits are either equal or they're disjoint, and the orbits partition the set X. We'll see in a little bit an application of this result, the fact that X is partitioned into orbits. Now there's another, so the orbits, they live inside the set X. There's another object that is important, or other objects that are important, and these are the stabilizers of the elements of the set X. So for a given element X, its type stabilizer, which is denoted by G subscript X, it consists of all the group elements G that fix that X. So G acting on X doesn't change anything. So G acting on X equals X. And we showed last time that the stabilizer of any element is a subgroup of G. Okay. So these are things we did last time, as well as this result. So we stated and proved it at the end of last lecture, what is called the orbit stabilizer lemma. And it says the following: if G is a group acting on a finite set X, and X is an element of it, then the cardinality of the orbit of X equals the index of the stabilizer of X in the group G, which, if G is finite, is the same thing as the ratio between the cardinality of G and the cardinality of G of X. Okay, so let's go over the proof of this result. So if we denote K being the index of this subgroup, and we consider K disjoint cosets of G of X, then the group G is partitioned into this coset. So you have we have these representatives A1, A2, AK, and G is a disjoint union of A1 GX, A2 GX, and so on. Okay. Now, if we examine the orbit of X, so we want to determine, the question for us is what is the cardinality of the orbit of X? So we want to see what is the number of distinct elements in that orbit. So before we look at distinct elements, perhaps a simpler question is to see when two elements from of the form G times X are equal. So that's what we argue here, that G if G and H, if we have G and H elements of G, then G acting on X is equal to H acting on X if and only if H minus 1 times G fixes the element X. And this is the same thing as, by the definition of the stabilizer of X, is the same thing as H minus 1 times G is an element of the stabilizer, G of X. And this is equivalent with the fact that the cosets of G of X corresponding to the elements G and H are the same. So we have that G of X acting is equal to H of X if and only if these cosets are equal. But now you can look at it backwards. These cosets are equal implies that G of X equals H of X, and if the cosets are distinct and automatically disjoint, then that means that G of X is different from H of X. So with that in mind, because the cosets above A1 GX, A2 GX, and AK GX are all distinct, that means that these elements of the orbits of X, A1 acting on X and all the way to AK acting on X, are distinct elements in O of X. And it turns out that these are all the distinct elements in O of X. And why is that? Well, if we pick an arbitrary element of the orbit, let's call it again G acting on X, then we have that G is an element of the group, but the group is partitioned into these cosets of the stabilizer of X. So the group element G has to land exactly in one of these cosets. So G belongs to the coset AL times GX for some L between 1 and K. And that means that G looks like AL, maybe I should erase it here, AL times G prime for some G prime, an element of the stabilized G of X. And therefore, when we look at the action of G on X, it's the same thing as AL times G prime acting on X. And this is by the second property, skip the step here, by the second property of the group action, this is the same as AL acting on G prime acting on X. But G prime is from the stabilizer, so that G prime acting on X is X, so we get AL acting on X. Okay, so it turns out that in the end, what we get is that the orbit of X equals A1 acting on X. We have this kind of bijection between the cosets and the elements of the orbit, the cosets of stabilizer GX and the elements of the orbit of X. Okay, so now let's do some examples to get more familiar with these concepts. So let's say the set, the group G is, let's say, S4, the symmetric group of permutation on 4 elements, and X is a set of 4 elements. So G acts on, so we can, there is an action of G, so G acts on X by the following action, by the following map, let's say, action. So we send every order pair sigma and X. So sigma comes from G, X comes from the set X, that's mapped to sigma of X. Okay, And I'm not going to check here, but I'll leave you as an exercise to prove that this is a group action. Okay, and so let's do a simple example. If let's say sigma is the permutation 1, 2, 3, 4, 2, 3, 4, 1, sigma acting on element 3 produces the element 4, because that is what sigma 3 is. So this 4 here is sigma 3. Okay. All right. So what can we ask here? Well, one question would be, what are the orbits? If I give you an element x, let's take some element, let's say 4. What is the orbit of 4? So the orbit of 4 consists, by our definition, is all the elements of the form sigma 4 as sigma goes through the permutation, all the permutations in S4, and there is a permutation that maps 4 to any, so for each element, 1, 2, 3, 4, there will be a permutation that maps 4 to that element. So the orbit here, it's the whole set. So this is 1, 2, 3, 4. And what is, let's say, the stabilizer of G4? So this consists of all the permutation in S4 that fix 4. So S4 equals 4. So these are going to be permutations that permute just the first 3 elements in any possible ways. And they leave 4 fixed. So this is a group which is isomorphic to the permutation group on 3 elements, S3. Okay. And you can see here that the previous result obviously is satisfied, that the cardinality of G, which is the cardinality of S4, which is 24, 4 factorial, equals the cardinality of the orbit of 4 times the cardinality of the stabilizer of 4, because one is 4 and this one is 6, cardinality of G4. Okay, so that was a simple example. Let's do another one, a little bit more involved. So here, let's take the set X to be the set of 7 elements. 1, 2, 3, 4, 5, 6, 7. And let's take as a group G. This will be a subgroup of S7, consists of the identity, which I denoted by epsilon. So this is the identity permutation. You can put a 7, but let's just leave it like this. And then the second one is a product of 2 cycles, 1, 2, 3, 4, times 5 and 6. Let's call this one tau 1. The second one is a product of 2 transpositions, 1, 3, times 2, 4. Let's call this one tau 2. And there's one more, is 1, 4, 3, 2. And again 5 and 6. Let's call this one tau 3. Now, so my claim is that G is a subgroup of the symmetric group with the 7 of degree 7. How does one prove that? Well, I'll leave it as an exercise for you to figure out that if you take the permutation tau 1 and you square it, we're going to get the permutation tau 2. And if you take the permutation tau 3 and you square it, you're going to get the permutation tau 2 again. Also, if you take tau 1, it's a product of 2 disjoint transpositions, so that's easy. This is going to be the identity. And the last one, tau 1 times tau 2 equals tau 3. So these things require a proof, but it's not too difficult to do it. You just have to check where each element is mapped, and yeah, so these are some of the relations between these permutations. Okay, so that's okay. So I define a group. I have a set X. Now, what is the? I have to define an action, and the action is the same as before. So, okay, G acts on X by, if I have sigma, an element in G and X an element in X, this is mapped to sigma X, the value of the permutation sigma at the element X, which is in X. And as before, exercise that this is a bona fide group action. And now let's try to figure out a few things. So we want to look at some orbits, and we want to look at some stabilizer. So perhaps it's good to write this permutation, these permutations on this page. So let me write them again here. We have epsilon 1, 2, 3, 4, 5, 6. 1, 3, 2, 4, and then 1, 4, 3, 2, 5, 6. So let's figure out some of these things. So for example, what would be the orbit of the element 1? So the orbit of the element 1 consists, by definition, of all elements of the form sigma 1, where sigma comes from the group G. Okay. And now this is our group. Our group, because of the properties of this permutation that we listed on the previous page, this group G consists of these 4 permutations. Identity leaves 1 unchanged, so 1 lives there. Now, the first permutation, which we call tau 1, this one here, maps 1 to the element 2, so that's okay. We add 2. This permutation tau 2 maps 1 to 3. And the last permutation here, this one tau 3, maps 1 to 4. So that's the orbit of 1. Now, I could calculate the stabilizer of 1 in 2 ways. So stabilizer of 1 consists of all permutations sigma in G that fix 1. And so you look at the permutation above, and it's only the identity. And again, you see that cardinality of G, which is 4, equals what? Equals the cardinality of the orbit of 1 times the cardinality of the stabilizer. It's 4 times 1. Orbit stabilizer lemma result there. Now let's do other orbits. Let's try the orbit of 5. Same as before. This is all the elements of the form sigma 5, or sigma an element of G. Well, the identity sends 5 to 5. Tau 1 sends 5 to 6. Tau 2 again fixes 5, so sends 5 to 5. And tau 3 also sends 5 to 6. So the orbit of 5 has 2 elements, 5 and 6. And you can guess now what the cardinality of G5 will be. All the permutation sigma in G such that sigma of 5 equals 5. What are they? They're going to be the identity and tau 2. And this is a subgroup of order 2 of G, the same as before. The product of these two sets is 2 times 2, which is the cardinality of G, which is 4. Let's do one more example. The orbit of 7. And these are all of the format sigma 7 for sigma element of G. And now the identity leaves 7 unchanged, and none of the other permutations do anything to 7, so they all fix 7. So the orbit of 7 is just this element 7. And Now, what is the stabilizer of 7? Well, as before, consists of all sigma in G that fix 7, and this is the group itself, G. Okay, so that's an example of group action. Okay. And that was our example 2. Let's do 3. Okay. Now, let's consider the following. Let's consider the following functions. F1 from the complex plane to the complex plane. F1 is the identity. F2, also from the complex plane. Complex plane. F2 of Z is minus 1 over 1 plus Z. And well, so we have to be a bit careful, so I'll define these functions. So here it's C minus 0 and minus 1, C minus 0 and minus 1, so we cannot have minus 1 in our domain. And F3, it's also from the complex without 0 and minus 1. F3 of Z equals minus 1 plus Z divided by Z. Okay, so here we cannot plug in Z equals 0. So we have a set G, which consists of F1, F2, F3, and I claim that G with the composition, usual composition of function, is a group. Now I leave you the details to prove this, but note that if you F1 is the identity function, well, yeah, pretty much you can consider it that. So maybe, yeah, let me put this here also from C to 0 without minus 1, from C to 0 minus 1. Okay, and now one can show that F2 composed with F2 gives us F3, and F3 composed with F3 gives us F2. Okay. So this is a group, and now we take as X the set, the complex plane without 0 and minus 1, and we can define an action G acts on X by the following. If we have some one of these functions, let's call it Fj, and we have an element X that is mapped to Fj of X for J in 1, 2, 3, and X. Okay. And now I leave you as an exercise to do some things. Try to calculate what are the stabilizers of G1, of Gi, where I is the I square equals minus 1, and G omega. Omega is a cubic root of unity, so it's E to the 2 pi I over 3. Okay, so this is a different action than the one that we're used to. So let me give you a few more examples and exercises for you to think about. So let me give you this example 4. Here, let's take G as the group of 2 by 2 matrices. Well, so they're defined as follows. So you have cosine theta times sine theta minus sine theta sine theta. Okay, where theta, we can take theta between 0 and 2 pi if you want. Okay, so G with matrix multiplication is a group. I recognize it's something to do with rotations. So again, you can prove this. It's not very difficult. And now we can define, so our set X is the Cartesian plane. And we say that G acts on X by the following. If we take an element G of it, so here the bracket will be a bit big. So if we take one of these matrices, and we act on it on the order pair XY, this gets mapped to, so X is the horizontal coordinate and Y is the vertical coordinate. This gets mapped to X cosine theta minus I sine theta and X sine theta plus Y cosine theta. Now I claim that this is a group action. Well, actually what it does, so again, exercise, what it does, it, so let's just see what this operation does to some vectors, some points. So if we take here the point of coordinate 1 and 0, that is going to be mapped. So for some theta, if we draw here our unit circle, so that's a circle. That will get mapped to this point of coordinates cosine theta, sine theta. So that's a counterclockwise rotation by an angle of theta. And this, so this is, so cosine theta, sine theta is what we obtain by acting with this matrix, with this matrix cosine theta, sine theta, minus sine theta, cosine theta, on this point of coordinates 1, 0. And it's not too hard actually to see that if we act on another element here on 0, 1, it's also a rotation of theta this way. This is going to be the point whose coordinates are going to be minus sine theta, cosine theta. Okay, so essentially, so this is what happens for these 2 points, but in general, what's going to happen is that when this matrix acts on this point, it just rotates the point counterclockwise by an angle of theta. So it's that's the meaning of this action. And now let's do a few things. What would be, for example, the orbit of an element, and what would be the stabilizer of an element here? So if we're looking at what is the orbit of, let's say, this point 1, 0, this will consist by of all the points of coordinates cosine theta, sine theta, where theta is a real number, or theta goes between 0 and 2 pi, and this is going to be the circle of radius 1 centered at the origin. So something similar will happen for the orbit of any element. The orbit of the origin is a little bit special, so I let you figure out what's the orbit of that. And now, what is the stabilizer? If we look at the stabilizer of 1, 0, that consists of all these thetas that will fix the point. So cosine theta sine theta equals 1, 0. And there is only one matrix that has that property, and that's going to be the identity. So it consists only of the identity matrix. All right, so now we have a bunch of examples. And so let's prove a couple of more results, and then let's see get to the questions that we stated in our introduction. Okay. So this is 5. Seven. Okay. All right. So let's prove the following. So we'll prove the following proposition. And G, let's just be a group acting on finite set X. Now, we need a notation, so I'll write it in a different letter. Denote fix of G consists of all those elements X of X that are with the property that G of X equals X for any G in G. So fix of G, it consists of all the elements of X that are fixed by every element of the group G. Okay. Now here I need a finite group. So let me erase here. So the conclusion is the following. Then the cardinality of the set X equals fix of G plus summation over all X. The property Gx is not the whole group stabilizer of the index G times G of X. Now this summation, so we'll talk about it, that it's, yeah, we have to, have to be a bit careful about it, but yeah. So what's the meaning of this result? Where does it come from? Well, this result comes from the fact that X is a union over all elements X of the orbits of X. So X is because these orbits are equivalent classes, they partition the set into these orbits. So the cardinality of X, because this is it's a partition, will be a summation over all X in X of the cardinality of the orbits of X. Okay. Now, when we have an orbit of X, we're gonna have two. When we sum up these orbits of X, we have two situations. Some orbits will have cardinality 1, and the rest will have cardinality not equal to 1. Okay. Now, what does it mean that an orbit has cardinality 1? So let me write it below here. So an orbit of X has cardinality 1. That's equivalent to what? Well, that's equivalent to the fact that So what is the orbit of X? It's everything that looks like G acting on X with G in G. This set has cardinality 1. Well, we know that one element of the orbit, it's X, because the identity of the group acting on X gives us X. So that's equivalent to Gx equals X for any G in G. And that is equivalent to what? That's equivalent to X belonging to fix of G. Okay, so now if we go back to this sum here, it splits. It has two parts. One is the summation over all X in X with the orbit of X equals 1 of 1 plus the sum of X in X, orbit of X bigger than 1, of cardinality here, of cardinality of orbit of X. And now what does this equal? So the first part, we are adding a 1 for every element from the fix of G. So here I have to put a cardinality. This is going to be cardinality of fix of G plus, on the other side, we have a summation over all X in X. The cardinality of the orbit from the orbit stabilizer lemma is the index of the stabilizer. And here, because the orbit is cardinality bigger than 1, then G of X is a proper subgroup. So it doesn't equal G. And here we also see this other thing, that X is in fix of G, even only if also that G of X equals G. Okay, so this is just a simple consequence of the fact that the orbits partition the ground set. And it has a variety of consequences. Let me give you first the theoretical one for groups, and then I'll give you some other ones for counting. If we apply the previous result to the action of a group on itself by conjugation, then we are going to get the following proposition, which is usually called the class equation. I mean, it's something to do about the conjugacy classes. So let G be a finite group acting itself by conjugation. We need to define what's fixed and what's the other one. So define Z of G. This is called the center of the group. It consists of all the elements G such that Gx equals Xg for every X in G. So it's called the center of G. And for this action, we'll see in a second, it keeps the role of fixed of G. And also we want to define for X in G, C of X is the conjugacy class of, it's the stabilizer of, this will be the stabilizer of X with this action. This consists of all G in G such that Gx, G minus 1 equals X. And it's the same thing as all G in G such that Gx equals Xg. So it's called a centralizer of X. Okay, then the class equation states that cardinality of G equals the cardinality of its center, Z of G, plus the summation over all X not in the center of the index centralizer int. And now the proof, the result follows on the previous proposition by noting that for this action, fix of G equals Z of G, the center, and G of X, the stabilizer of X, is, with this action, is the same thing as the centralized C of X. Okay. So there's one more result that is quite important, which is a Bernstein lemma, but we'll do that in a little bit. But let me give you some applications of this result. Okay, so let's deal with some consequences. Okay, one. So let's take P is a prime, and N is a natural number. And we want to prove that P divides N to the P minus N. Okay. So consider the group G, which is ZP. But when we started in the previous lecture, at the beginning, we had some examples. And we show that GP acts on the set X of all P tuples, X1, XP, with X1, XP in the set 1 to N by shifting, by a shift action. Remember that. So we have ZP, which consisted of, we call it 0 hat, 1 hat, P minus 1 hat. So 1 hat will act of X1, XP by shifting to the right by 1 unit. So you get XP minus 1. 2 hat acts by shifting by 2 positions, and so on. Okay. Now here, and the natural number. Okay. So now the previous proposition. So this is a legit action. So the previous proposition, this one tells us the cardinality of X is going to be fix of G plus the sum of these indices. So what is the cardinality of X? Well, that's pretty easy. So let me state first this result. Cardinality of X is the fix of G plus summation over all X in G, X in X, G of X not G of the index Gx, the other way around. GGX. Okay, so now what is this one? We have P tuples coming from a set to 10 elements, so this is N to the P. Now, what is this one? Fix of G. So what are the P tuples that are fixed? So those are the P tuples that no matter how you shift them, you get the same value. So those are going to be the P tuples in which all the entries are equal. So what I'm saying here is that fix of G will consist of all things that look like X, X, where X comes from this set with n elements, and there are n choices for X, so that's n. Now plus, here, what type of terms are we going to get here? Well, G consists of the integers mod P with addition, and the only subgroups of this group are 0 and the group itself, G. Now here we're taking the index of a subgroup Gx, which is not G itself, so that means that this subgroup Gx has to be 0. So in that case, the index is going to be equal to P. So what do we get on this summation? We're going to get multiples of P. We're going to get P times a certain number of times T times. Well, what does this imply? Well, it implies that the difference NP minus N is a multiple of P, so P divides NP minus N. So this is a proof of Fermat's little theorem using group actions. And now let's let's do another application, which involves the Cauchy's theorem. Which was the one that if we have G, a group of order n, P a prime, such that P divides the cardinality of G, which is n, then there exists an element X in G such that the order of X is P. So order of X is P means X to the P equals the identity in G, and X to the, let's say, K doesn't equal the identity of G for any K less than P. Okay. Okay. So, okay. So here, it's a similar action to the one from before. It's another action that we describe at the beginning of the previous lecture. So the group here acting is going to be G itself. So it's not going to be the Z mod P as before. The set X will be a little bit different too. Will consist of all P tuples with the property that the product X1 times XP equals 1. Okay, so these elements Xi come from G. Okay, and now how does the action go? No, I was wrong. Like here, the action again, it won't be G acting on this P top. This is a set X, and it will be the same ZP, which is integers mod P, acts on X as before. So 1 hat X1 XP is going to give us XP X1 XP minus 1. Now you have to be a bit careful here when you prove that this is an action, because it's not enough just to shift these elements to the right. You have to prove that the product stays 1. So initially we have that X1 times XP equals 1, and then if you multiply by XP inverse to the right, we get that X1 times XP minus 1 is going to be XP inverse. So this is multiplication to the right. And now we multiply to the left by XP, and we get that XP times X1 times XP minus 1 equals 1 of G. So this is a legit, again, this is a legit group action. And by the previous result, we have that the cardinality of X should equal the fix of G plus the summation over all X in X with G of X not equal to G of this index. Okay, now what can we say about each of them? What is the cardinality of X? Well, in X, we have all these P tuples. We won't have n to the P anymore because there's a relation between them. But if we pick P minus 1 of these elements, let's say we pick the first P minus 1 elements, we have n choices for X1, n choices for X2, n choices for X to the XP minus 1. And for each such choice, XP is determined from this equation. So the cardinality here is n to the P minus 1. Okay, now what is fixed P of G? Well, here, what are we counting? Let me write it like this. We will count all the P tuples that are fixed by this action. So they're going to be all the elements of the form XXX, with the property X times X times X equals 1, which is X to the P equals 1. So here we will have all the elements of, this will count all the elements x in G with the property that x to the p equals 1. Okay, so we have n to the p minus 1 equals this, and then plus. Now here the situation is the same as before. Our group G is ZP, and G of X as a subgroup can only be ZP or the subgroup of order 1, but because so from here we're going to get that G of X has to be 0. So here we'll get a multiple P times some number T. So now we have P, a multiple of P here. N is divisible by P. Therefore, this set has to have a cardinality which is divisible by P. So let me write on the top. So we'll get that P divides the cardinality of all the elements x in G such that x to the P is 1. Now, this cardinality could be 0, but it's not going to be 0 because this number is non-zero, because the element 1G to the power P gives us 1G. So this is 1G here. So we have that this cardinality here is non-zero and is divisible by P. So there has to be at least one other element there, which is not identity, that has the property that its P's power equals 1. And actually any such element is going to have this, its order is going to be P. You can prove by contradiction that the order cannot be any other number. Okay, so I'm out of time for this lecture, but next time we will discuss Burnside's lemma, and we'll do some of its applications, and that will be the last lecture on enumeration, and the lecture after that will start graph theory.